From the University of British Columbia, I'm Martin Ordóñez, and this is Power Electronics. Today, we're going to talk about thermal management, and we have an invited speaker who's going to explain how to select a heatsink.
Hello everyone, my name is Ruhollah Shafai and I'm a researcher at UBC. My research consists on detailed thermal and electromagnetic modeling and analysis of magnetics in high-frequency power converters. But now we are going to take a look at simplified thermal calculations for thermal management in power electronics. Today, we are going to talk about the different heat transfer mechanism focusing on thermal conduction. We will also see how we can analyze its effects on the thermal design of power electronic devices, such as heatsink design and selection. Our goal is to solve a common power electronics problem from the thermal point of view, determining the steady-state temperature of the junction of a device when employing a specific heatsink. As you can see, we have a MOSFET connected to a heatsink through a thermal conductor, and we want to calculate the operating temperature in different points. But first, let's take a look at some thermal concepts. Heat is the amount of energy that is transferred from one system to another, or between system and surroundings, as a result of temperature difference. Energy transfer originates from the random motion of molecules. Mainly, there are three different heat transfer mechanisms: thermal conduction, thermal convection, and thermal radiation. Heat transfer processes can be quantified in terms of appropriate rate equations. In this video, we are going to focus on thermal conduction. For heat conduction, the rate equation is known as Fourier's law. In a one-dimensional problem, the heat transfer rate, or heat flux, in the x direction per unit of area can be expressed as follows. Heat flux Qx double prime is equal to negative K times dt by dx, where the heat flux is directly related to the thermal conductivity, which is known as a K, and the temperature difference versus x. The parameter K is a transport property known as the thermal conductivity and is a characteristic of the material. The negative sign is a consequence of the fact that heat is transferred in the direction of decreasing temperature. That is, from the side with higher temperature T1 to the side with lower temperature T2. It should be noted that the temperature gradient can be linearized by using the temperature difference of 2 points. That is, the temperature gradient can be expressed as T2 minus T1 over the length L, which can be represented as negative delta T over L. That is, we can consider dt by dx as the temperature difference delta T between two difference points divided by the distance between these points. The heat flux can also be expressed as total power loss per unit of area. Therefore, we can find a relationship between the heat flux through conduction as power loss, P loss, is equal to K times A over L times delta T. Or we can rewrite it as P loss is equal to delta T over L over K times A, where delta T is the temperature difference between 2 points, L is the distance between these points, K is the thermal conductivity, and A is the unit of area. It can be a little complicated to understand and solve these non-electrical parameters and equations. In order to make things clearer, we can analyze these non-electrical mechanisms with very familiar and known electrical concepts and simple circuits. Let's take a look at a very simple electrical circuit. When current flows through a resistance as shown, a voltage drop between the terminals of the resistance is created. The relationship between the current, the resistance, and the voltage follows Ohm's law. I is equal to V over R. In an electrical circuit, the reference point is the ground, which has zero voltage. Now let's compare the mentioned Faraday's law with this electrical circuit and equation. Since heat or power loss is related to the flow and displacement of molecules, it can be considered as loss current. Actually, the produced loss inside of a device leads to a temperature difference compared to a reference temperature. The reference point depends on the connection of the component. So, if the temperature in the thermal circuit is compared to the voltage in the electrical circuit, and the power losses in the thermal circuit are compared to the current in the electrical circuit, then a similar relationship to Ohm's law can be determined. Therefore, an equivalent thermal resistance can be defined as L over K times A. This way, there is an analogy between the electrical and thermal phenomena. As you can see, the relationship between power loss, flow, and temperature change is quite similar to the relationship between current flow and voltage drop. Recall that the thermal equivalent of the electrical resistance is called thermal resistance. Pay attention that the unit of this resistance is related to thermal characteristics. Its unit is defined as degrees Celsius per watt, as it represents the temperature difference over power losses. From the equation, we can see that just like in an electrical resistance, thermal resistances are inversely proportional to the surface area. In analogy to electrical resistances, lower values of thermal resistances imply that the conduction of losses is more efficient and better thermal performance can be achieved. Therefore, knowing the heat source value, which is the losses of the circuit, and the thermal resistance values, we can analyze and manage the temperature of a specific component or a circuit. It should be noted that this thermal resistance should be calculated for each component or part in your circuit. This means that for each connection in your circuit, you have to calculate a thermal resistance. Let's go back to our problem, the simple electrical circuit including a heat-sinked power MOSFET. We want to measure the temperature of the junction of the MOSFET and see how we can select the proper heatsink for the proposed power switch. Based on the analogy between the electrical and thermal phenomena, we can create an equivalent circuit that represents the physical device. Let's take a look in more detail to the problem. A MOSFET is connected to a heatsink via a proper thermal conductor. The heat produced inside the MOSFET goes through the materials and then is dissipated by the heatsink. Therefore, we can define three different resistances between the junction of the MOSFET and the ambient temperature, which is taken as reference. The red one, R theta JC, is the thermal resistance between the junction of the MOSFET and its case. The blue R theta CS represents the resistance between the case of the MOSFET and the thermal heatsink. The green R theta SA represents the thermal resistance between the heatsink and the ambient. Because heat loss flows through all the materials, the current source represents the power losses. In order to solve the thermal problem and find the junction temperature value, as mentioned before, we need to know the thermal resistances. and the power losses, which act as the thermal source. For determining MOSFET losses, you can watch our video on power loss calculation. However, for this example, let's consider 6 watts of losses. It also should be noted that T1 is a reference temperature defined as the ambient temperature, which is considered to be 25 Celsius. We will consider 3 different scenarios for our problem. First, a power switch will be used without any heatsink. Second, the power switch will be connected to a heatsink with just natural cooling. And at last, a forced cooling system for the heatsink will be added. So, then we can compare our results. Let's choose a MOSFET. In this example, I am using the TO220 MOSFET. If we take a look at the datasheet of the MOSFET, we can find a table with the thermal information for the component. For our selected device, there are 2 different thermal resistances, which are related to the mounting of the device. The first one is for when there is a heatsink connected, and the last number refers to when there is no heatsink attached to the MOSFET. Therefore, we have the junction to case or R-theta-JC resistance for when we are employing a heatsink, and R-theta-J ambient for when we are not using a heatsink. Let's first consider no heatsink. In this case, the problem has only one thermal resistance. According to the datasheet, the conduction resistance between MOSFET and ambient is 62.5 degrees Celsius per watt. Considering the ambient temperature of 25 degrees Celsius and 6 watt as the heat source, the temperature of the junction can be calculated by multiplying the thermal resistance by 6 watt, which is the heat source, plus the ambient temperature. The resulting temperature is of around 400 degrees Celsius, which is a very high temperature for this kind of application. For this reason, we have to select a proper heatsink to allow for adequate temperatures of operation. There are 3 different types of heatsinks. Heatsinks should be selected based on the temperature management and limitation of each component. Usually, E-series and W-series heatsinks are used for power electronics switches. Okay, let's select the E-series with 51 mm height for our example. In order to solve our problem, we need the datasheet of the heatsink. You can always Google the heatsink's part number and you can find its datasheet. There is a graph in the datasheet which shows heat dissipation characteristics. Now, you can see different curves in the graph, since we can select different heights for the heatsink. Let's try with the E51 that has a height of 51 mm. As you can see, we have 2 curves for the E51. One curve, which is from the top left side to the bottom right side, shown in red, and another one from bottom left side to top right side, shown in green. The first one is for the forced cooling system, which is when a fan is connected to the heatsink, and another one is for the natural cooling system, when there is no fan connected to the heatsink. First, let's try with natural cooling system. As mentioned before, we have 6 watts of losses as our heat source. So, by using the proper curve, the green one, the surface temperature rise can be determined around 49 degrees Celsius. Now, the thermal resistance of the heatsink can be calculated by dividing 49, which is the temperature rise, by 6, which is the power loss being dissipated by the device. So the resulting resistance is 8.16 degrees Celsius per watt. Pay attention that this value is calculated based on ideal conditions in which the environment temperature doesn't change, the heatsink is completely connected to the MOSFET, etc. In order to account for uncertainties, it is better to apply a safety factor of 20 to 30%. In this case, I will consider a 30% safety margin. Therefore, a new value can be calculated for the resistance. Pay attention that if you change the power loss value, the resistance must be calculated again. As mentioned before, in order to have a proper connection between the MOSFET and heatsink, a proper thermal conductor should be used. The thermal conductor can provide a good thermal contact between the MOSFET and heatsink to make sure that all the area of the MOSFET is properly connected to the heatsink, and also ensure that the MOSFET is electrically isolated from the heatsink. The thermal resistance of the thermal conductor depends on the material you select. Here you can see the value of thermal resistances for different common materials used as thermal conductor. Let's select the silicon pad for our example, which has 1.1 degrees Celsius per watt for the conduction resistance. Now, we can go back to our problem, which is the heat-sinked MOSFET. As calculated, we have the two thermal resistances, R theta SA, which is equal to 10.62 degrees Celsius per watt, and R theta CS, which is equal to 1.1 degrees Celsius per watt, since we have selected the silicon pad as our thermal conductor. Pay attention that in this case the MOSFET is connected to the heatsink, so we have to select the proper value of the thermal resistance between junction and case from the MOSFET datasheet. Let's go back and take a look at the thermal table of the datasheet. You can see that for the TO220, the junction to case resistance R theta JC is 0.83 degrees per watt, since we have a heatsink connected. Now we can solve the problem by using a very simple electrical calculation. The thermal resistance R theta JC is 0.83 degrees per watt. By considering 25 degrees Celsius as the ambient temperature or reference voltage, and using the heatsink's calculated thermal resistance times the power loss of 6 watts plus the reference temperature, we have 88.72 degrees for the temperature at the heatsink. By applying the same procedure for other resistances, we can calculate the temperature value of the MOSFET. The calculated value for the junction is 100.3 degrees Celsius, which is 75.3 degrees Celsius higher than the ambient temperature. Remember that without heatsink, our junction temperature was 400 degrees Celsius. We can see that by adding the heatsink, we have managed to lower the temperature to a tolerable level. Now, for the last case, let's consider a forced cooling system for the heatsink. Let's take a look at the heatsink's thermal curves. In this case, we have to look at the top and right axis of the graph. You can see that we need the air velocity of the fan. You can calculate this parameter with the data sheet of the fan. By considering 400 feet per minute as average air velocity of the fan, the thermal resistance can be determined. We can observe that it is around 4.5 degrees Celsius per watt. Make sure that you use the right curve and axis for forced cooling. Again, don't forget to apply a safety factor. By applying 30% as safety factor, we get to 5.85 degrees Celsius per watt, which is much lower than the previous case with natural cooling system. Now we can go back to the equivalent electrical circuit and apply the changes due to the change in the heatsink thermal resistance. Again, consider 25 degrees Celsius as the ambient temperature, using the determined thermal resistance for the heatsink times the power losses of 6 watts plus the reference temperature. Now we have 60.1 degrees for the temperature at the heatsink. By doing the same procedure, we reach 71.68 degrees Celsius for the MOSFET junction's temperature, which is about 47 degrees higher than the ambient temperature. Remember that by using natural cooling, we got to 100 degrees Celsius. So, as you can see, you can manage the operating temperature of your device by determining a proper heatsink before doing any experimental work. In this video, we provided an example for the steady-state thermal conduction analysis of power electronic circuits. Stay tuned for examples of convection and radiation thermal analysis.
Today, we talked about thermal management, operating temperature, and how to select the heatsink. If you want to see more videos on power electronics, please check our channel.